Okay, so since we just finished chapter 2 last time, I'd completely forgotten that if you look in Brightspace, you'll see that I posted some review problems to get us some practice with what we learned in chapter 2. You'll find them, hold on, at the end of chapter 2. Um, There we go. Chapter 2 review problems, right? So it's just a bunch of questions based on exactly what we were doing. So I put it there so that you get some extra practice. So I'd like to go over those questions right now, and then we can dive into the new material. Okay, so you can see that we have 13 problems taken from chapter 2. And if you can do these, you could probably do anything that the WebAssign might throw at you. So why don't we start with this first one? Now, of course, oh, and one more thing, I also put together a very handy list of all the rules that we learned, rules of differentiation, and they're also here on Brightspace. Where are they? There they are. It's called the rules of differentiation. So I sat down and I wrote them all. It's nice to have everything in one place. That's my opinion. I like to keep things organized. So I wrote them all down so they're all in one place. If you want, you can print this out and use it while you're doing your assignments. And I also put some of the trig functions down here because, again, you don't want to be constantly going back to the book and looking for all this stuff or going to the internet. It'll be so much quicker if it's all just sitting here in one convenient location. Anyway, so let's get to it. So we start here. Now, clearly, because this is a polynomial, this is a job for the power rule. Let's go find our power rule. And so in other words, when you have something like this, x to the n, you will end up with, let me just write it right here. Now, if you also happen to have a constant involved, which we do here, when you combine that with the constant, you'll end up with n times c times x to the n minus 1 power. Okay, so the constant basically doesn't affect anything. In fact, you could even factor it out if you want to. In other words, you could, instead of writing like I did here, what you could do is this. And then just whatever your derivative is of x to the n, you just at the end multiply by c. So you would end up here with c times nx to the n minus 1. And then you'd end up here. And of course, it's the same thing. So here we have 4x squared. We can factor out that 4 if we want. And now we'll apply the power rule to x squared. And we ultimately end up with 8x. Okay. So that wasn't so bad. All right, great. We're off to a good start. Now the second one is very similar, except that it has two terms in it. Now, of course, we know that there is a sum rule and a difference rule, which simply tell us that if you have the derivative of a sum of functions, the derivative of that sum is the sum of the individual derivatives. And with the difference rule, if you were trying to calculate the derivative of a difference of functions, what you're basically doing then is taking the difference of the individual derivatives. All right, so that's what's going to happen here. So we're going to differentiate this. So the derivative of 5x minus x squared can be broken up into two pieces. And now we can apply the power rule to what's inside the brackets. And so now keep in mind that x is the same thing as x to the first power. So when you apply the power rule to x to the first, you're going to get 1 times x to the 1 minus 1, which is 1 times x to the 0, which is just 1. Okay, so that means here we have 5 times 1. And then here, when we apply the power rule, we'll have 2 times x to the 2 minus 1 power. And so you're going to have 5 minus 2x to the first, which is simply 5 minus 2x. All right. So now, of course, after a while, you'll know this like the back of your hand, and you won't have to necessarily go through all these steps. But whenever you have simple derivatives like these, especially with the polynomials, you're essentially using the power rule and constants to get to your results. Now, actually, these are not too much more complicated. It's just that there are more terms. But again, this first one is a polynomial. It's a fourth degree polynomial. So we can break it up into 3 terms. So in the first case, actually, what I'm going to do is factor out that 8. Oops, hold on. So this last one is a constant. So it's just going to go to 0. Remember, the derivative of a constant, that's our actually first rule on this list, is just 0. So I'm going to wind up with 8 times 4x to the 4 minus 1 plus 9, 2x to the 2 minus 1 minus 0. And we're done. Okay. This one's a little bit more challenging because you've got x in the denominator. So I think your best bet here is to rewrite this as x to the 4th plus 2x to the minus 1 power. I personally think it's easier that way. You don't have to, but I think it's a smart move. So we'll end up with this. Okay, great. Now, here we apply the power rule for x to the 4 minus 1 power. Now here, we're going to have minus x to the minus 1 minus 1. So it's going to be 4x cubed minus 2x to the minus 2 power. And if you feel so inclined, you can write it as, if you prefer, you could write it as 4x cubed minus 2 over x squared. Either one, of course, is fine. All right. What about this one? Now, all of a sudden, ooh. Yeah, so what's going to happen here is we're going to have to use the product rule. Now, the product rule is kind of complicated compared to what we've done up to this point. So let's review what it looks like. So if you have the derivative of a product of functions, this is how you calculate that derivative. So you've got, let me just repeat it right here. And I just want to remind you that the prime means the derivative. So in other words, f prime of x is the same thing as dy dx. So, and the same thing with the g. So we have the first times this derivative of the second plus the second times the derivative of the first. Okay, great. So here, this is our f of x, this is our g of x. So, especially if it's a messy problem, you might want to write these out first. So here, we're just going to get 1. All right, the derivative of x, as we just saw a little while ago, is 1. The derivative of a constant is 0. So here, g prime of x, we're going to have 4x based on the power rule. And then the 3 just drops out. It's just a 0. So now all we have to do is substitute. So the derivative is x plus 2, 4x plus 2x squared minus 3 times 1. Now, if the expression is unusually messy, it may or may not be necessary to consolidate them all and simplify. Sometimes you can just leave it the way it is. But here, this is a very straightforward result. So we'll just go ahead and expand it out and see what happens. So here we're going to have, we have to multiply 4x by both of these terms. 4x squared plus 8x plus 2x squared minus 3. So we can consolidate 2 of the terms. And that's our final result. All right, it's not going to get any simpler than that. So it's a second degree polynomial. And also, by the way, I just want to remind you that at the end of each of these, you can confirm your results. Well, I mean, of course, you can just go ahead and double check, but you can always do that. So you don't have to, but it might be a good idea to go through and revisit all these rules and make sure you understand what you've just done. Now, the quotient rule is even messier than the product rule. Wow, look at that mess. So here's what you have to do. So we have a ratio of 2 functions. And so this is the rule. And so in this case, of course, the numerator is the f of x. 4x cubed minus 2x plus 1. So the derivative, based on the power rule that we saw earlier, is this 12x squared minus 2. G of x is x squared. And so g prime of x, again, based on the power rule, is simply 2x. So now we can go ahead and do some substitutions. X squared, 12x squared minus 2x, minus 4x cubed minus 2x plus 1 times 2x. And we'll divide that by 2x quantity squared. All right, so we can simplify this a little bit. And like I said, sometimes it'll prove not to be completely necessary. We could just leave it like this. But again, we have a relatively simple result, so we may as well go ahead and see if we can simplify it. 12x to the 4th minus 2x cubed. Now, here we got to watch it because we're multiplying and subtracting at the same time. So we're going to have minus 8x to the 4th plus 4x squared minus 2x. And this is 4x to the 4th. Okay. All right, so there should be some terms that we can consolidate. There's 2, yeah, here we go, these 2. And it looks like that's it. Now, you notice how all the terms have at least have x in them. So we can just simply divide that out from the numerator and the denominator. So there's the numerator and the denominator have a common factor of x, which we can now divide out. And that reduces this to 4x cubed minus 2x squared plus 4x minus 2 all over 4x cubed. But beyond that, I don't believe there's any way we can simplify this any further, so we'll just leave it like this. All right, now, oh boy, the trig functions are getting involved. And that can make things a little trickier. And that's one of the reasons why um, I did make up this list of trig derivatives. So here we've got two terms. Well, the first one is a polynomial. The second one clearly is not. Actually, I'm sorry, there's three terms. The third one is simply a constant. So the only one we have to keep an eye on is the secant. So f prime of x will be 2x. So if we look at our table, the secant's derivative is here it is, secant x tangent x. And of course, this one is 0. So the final result is simply 2x minus secant x tangent x. All right. Now this next one is even going to be a bit messier because not only does it involve a trig function, but it involves the product rule. Wow. All right. So let's see what we can do with this one. So f of x is the x squared. So based on the power rule, f prime of x is 2x. G of x is the cotangent. And again, I very helpfully put this on a chart here. That would be negative cosecant squared x. Well, all right then. Okay, so yeah, right here, negative cosecant squared. So now we plug in our results. We have x squared, negative cosecant squared x, plus cotangent x times 2x. Now, in a case like this, realistically, I don't believe that there's any way you can simplify it. So again, this will be our final answer. Now here we go. A trig function and the quotient rule both combined. Well, all right, let's see what we can do with it. Once again, here's what the rule looks like. So the numerator is the secant. And f prime of x, so we'll go back to our chart. What's the derivative of the secant? That's going to be, here it is. Oh, we saw this earlier. The secant times the tangent. G of x is just x, so that's easy. G prime of x is 1. All right, so let's plug in everything. X, secant x tan x minus secant x times 1. Okay. And if you want to, you could factor out that secant. There may not be any really that's if that helps to simplify it, then it's very important. But in this case, I don't think so. We can just write it as secant x um, times x tangent x minus one. Now, the reason why sometimes this is helpful with trig functions is because there might be an identity in here somewhere that we can take advantage of. Not here, obviously, but um, we'll get into that later on. But there are a lot of trig identities, as you may remember from your past travels. And sometimes if we can rearrange something in terms of those identities, we can reduce our results to something more simple. Not here, though. Okay. And we're done. All right. Now the chain rule. Now the chain rule is something that takes a lot of practice to get used to it. So basically what's happening with the chain rule is that you are calculating the derivative of a composite function. So if you remember how that works, all right. The other option we have is to identify a U term. And you'll get the same result. Now, let's try that here. All right. Now there's a six. Now the six is a constant, so we can basically factor that out. Um, and then here's what we could do. Think of this as U. And then we have du dx is 7. So that means what we're actually differentiating is think of this as u cubed. Okay. So if we've defined u to be 7x minus 4, what we're actually doing is taking the derivative. I've moved the 6 on the outside of u cubed. So that makes it a little easier to see that we're just using the power rule. Oh, no, I'm sorry. You know what we forgot to do? We forgot to write out the definitions of, see, for this definition, we need to know dy du and du dx. So let's do that right now. We have du dx. What I forgot to do is write down du dy. So in other words, since this function is 6 times u cubed, or if we're thinking just in terms of this, okay, so that means we're going to have 6 times dy du times du dx, which is 7. So we're going to have, let's see, u is defined as 7x minus 4. Let's just plug that back in real fast here. Seven x minus 4. And then we can multiply out. So you can see we're going to have 6 times 3 times 7. And that's equal to 126. All right. So that's that. Now, of course, it's not the only way to do this, but I do like the dy du approach because you can break it up into smaller pieces. Um, I mean, you could do it like this, but I don't know. I kind of like the dy du approach. And then here's another one. So let's try. If we let u be the 9x plus 2, um, dx is 9. And then the function itself, the tan u, the derivative of the tangent, by the way, is from our table, secant squared. Okay, so remember how this works. dy dx must equal dy du, which is secant squared u, times du dx, which is 9. And of course, u itself is 9x plus 2. Okay, so, and now, oh God, implicit differentiation. Yes, we had a lot of fun with that the other day. So if you notice here, these are the cases where the function cannot realistically be split up so that y is on the left and x is on the right. So that means we have to apply the chain rule every time we run across the derivative of y. So here, for example, you'll have 6 times 2x. Now for the y, we're going to have 3, 2y, dy dx as a result of the chain rule equals 0. So in other words, when you're differentiating y with respect to x in this case, you would normally have 3 times 2y. If that was an x, you would have 3 times 2x and you'd be done. But because it's a y, we need that extra dy dx as a result of the chain rule. Okay, and then you're going to have 12x plus 6y dy dx equals 0. And then you can subtract the 12x from both sides. And then we can divide it by the 6y. And of course, you can reduce this if you want to minus 2x over y. And that's it. That's the final answer. And if you notice, the final answer is in terms of both x's and y's. And because of the way the function was written, it's not realistically possible to split them up like we normally would. And then one more of these, and then we can move on to something else. Now this one we want to look at separately because this x squared y requires the product rule and the chain rule for the y. So that's a little bit trickier. So remember how the product rule works. You're going to have the first times the derivative of the second plus the second times the derivative of the first. Okay, so remember how that works with two functions of x. So you can think of it as the first term times the derivative of the second term plus the oh, sorry, I did this backwards. Hold on. It's the first times the derivative of the second plus the second times the derivative of the first. And that's what we had to do here. So, but that's just the x squared y. We also have to deal with y and 7, -7. So that means that what we're going to end up with is this. So we already know that on the left-hand side, we have x squared dy dx plus y times 2x. On the right-hand side, the derivative of y in this case is simply dy dx, and then we have the 0. All right, so now we can consolidate these. So I'll subtract the x squared dy dx from both sides. Factor out the dy dx. And then divide both sides, of course, by that 1 minus x squared. And at long last, you're done. All right, so I'm hoping that what you're seeing here was helpful in further understanding how these rules work. More practice is good practice, especially something like this. It's like learning the piano. You can't learn without actually playing the piano a lot. So it's the same thing here. You're not going to learn differentiation without learning, without practicing it on a regular basis. Okay. Anyway, so that part is done. So now we can move on to chapter 3, which we just briefly touched on the other day. And I remember we had this discussion about what the word extremum means. An extremum can either be a maximum or a minimum, and the extrema is the plural of extremum. All right. So how do we find them? And by the way, in applied areas, this is a very major topic of discussion. How do you find the largest or the smallest value of a function over a given interval? Because, like I was showing you the other day, that might help us figure out the maximum profit we can earn from selling our product, or it could tell us how to find the minimum cost, or something other very, very useful. So, all right, so let's see how that works. All right, so the first thing they mention here is, and by the way, I just want to mention a function doesn't have to have either. There's no guarantee that there's a minimum or a maximum. So we're going to be considering the minimum, of course, means the smallest value over a given interval. The maximum is the largest value. These are easy to identify with parabolas. And so here's the example they gave us. And so in these cases, we're looking at the interval from -1 to 2, but in the one on the left, it's a closed interval, which means we include the 2 endpoints. On the right, we do not. Now, on the left, the minimum you can see is the 0.01. The function does not fall below that anywhere in this interval. On the right, it's the same thing. So they agree on this. Where they're different is that here, the maximum is at the 0.25. Over here, that's not our maximum because it's not technically part of the interval. It's an open interval. So they're not telling us what the maximum is, but they're telling us that it's not this point. Okay. So in general, oh, here we go. So they're giving us an interesting case. So now look what happened here. This one has a closed interval, just like this one on the left, except at the point 0, where x equals 0, we have instead of the function equaling 1, it's defined to have 2 separate values. It's a piecewise function. And when x is exactly equal to 0, the function is actually equal to 2. And so that means that whatever this is no longer a minimum, okay, because it's not part of the curve. Now we can still find a minimum, but it's not zero. Now, according to this theorem, the extreme value theorem, as long as a function is continuous on a closed interval, then it has a maximum and a minimum. Now, when you get to a much more advanced course, like Calc 4 or whatever, they'll ask you to prove this, but for now, it's enough to just know it. Yes, if you keep going down this path, eventually you'll start becoming responsible for proofs because, at some point you have to know how to do that. You have to be able to show that a result is true for all values of X, for example. But anyway, so they're going to show us these two cases. Now, it says we should use a graphing utility to find them. All right, let's give that a shot. Let's go to Symbolab so that you can visually see. And by the way, Symbolab will tell us anyway. So we'll start with X squared X squared minus 4X plus 5. Now, I don't know if it's possible to ask Symbolab to only show it to us over a given interval. Um, I mean, I've never tried it. All right, let's find out. Maybe we got lucky. Oh, I don't know. What did we ask it for? -1, +3. No, you can see it went way past 3. All right, so it disobeyed me in that sense. I wasn't sure if it's capable of doing this anyway, but you can see for yourselves the maximum is right here. And they usually tell you, there it is. It's at the point X equals 2, Y equals this number. Wow, well, that doesn't look right. Hold on a second. -1 to 3. Well, we know that it's a parabola. You know what? I don't think they even drew it right. What happened? Because it's facing down. That's not right. Oh, no, something's wrong. X squared minus 4X plus 5. Yeah. All right, let's try that again without adding anything to it. Yeah, it must have confused it. This is what it looks like. And so, I mean, of course, we're only interested in the interval between -1 and +3. Maybe we can estimate that. Hold on a second. So, since the function is here, y equals, all right, let me write it as f of x. So at the left-hand point, f of -1 is -1 squared minus 4 times negative 1 plus 5. It's 10. So I didn't quite get that. It's up here somewhere. I chopped it off a little too soon, but this is approximately the point. Negative 1, 10. Okay. Now, what about 3? 9 minus 12 plus 5 is 2. All right. So, and this is where our interval begins and ends. All right. So, in other words, we're only interested in what's going on in here. Now, you can see that this is the maximum. It doesn't get any higher than that. The function, the graph doesn't go any higher than that. So, this is going to be our maximum. This point is clearly going to be the minimum. When x equals 2, the function equals 1. That's going to be our minimum point. Now, of course, we're going to use very sophisticated techniques to find these points. We're not going to be looking at a graph, but to get this ball rolling, they want us to just look at the graphs and see if it makes sense where to find the minimum and maximum points. All right, what else did they give us? Same one, same interval, but a different function. So this one is a cubic function, so it's going to behave very differently. Same interval. All right. So let's just quickly evaluate it at those 2 points before we get the graph. So this is minus 2 times positive 1, minus 2. And then f of 3, also negative 2. All right. So let's graph this thing. Okay. So all right, so I'm going to copy this part. So as I said before, this is a cubic function. So it has this very interesting shape. They have it curves up and then down. It's like a roller coaster. And the points that we identified, minus 1 corresponds to negative 2. That would be here, it looks like. And then 3, Okay, what happened there? Hold on a second. It's supposed to be -2. Well, it's hard to be sure with this graph, but no, sometimes when you hover over it, it shows you the points. You know what? I think it's where it's crossing. It looks like 3, but it's not quite there. Um, yeah, I think that's why it looks off because it's really close. This is slightly more than 3. It's like 3.15. So 3 is here. Yeah, okay, now we're good. All right, so this is the range that we're looking at. You can see there's a minimum way down here. And because it's a closed interval, um, it looks like this is our maximum. Now, they're not giving us the answers here. I think we can ask Symbolab, though, to identify them. Yeah, you can see here it is. See, the minimum is this god-awful thing, 2 plus radical 13 over 3. So our graph, we're only getting approximately the maximum and minimum values just by looking at the graph. To get the exact values, we need much more sophisticated techniques. But again, it's kind of helpful to look at the graphs the first time you're learning something. But here what they want us to see. Now, here's a more straightforward case. X cubed minus 3x squared. They chose this, I'm sure they chose this on purpose to make it work out nicely. X cubed minus 3x squared. So let's look at the graph. Yeah, that's more like it. See, this point is exactly 2, -4. This is 0, 0. This is 3, 0. Yeah, this is a nice function. All right, so we'll label these points. Now, the interval they're interested in is, oh, well, they didn't specify. I guess they're interested in the entire function itself. In other words, over the entire domain from negative to positive infinity. But they want you to see visually that we do have a minimum and a maximum because the curve rises until it hits 0, 0, and then it turns down. And then it falls, it hits 2, -4, and then it goes back up. After that, it goes up forever. So as x increases, the function goes to infinity. Down here, as x decreases, the function is going to negative infinity. So these are the 2 points of interest. This is our maximum. This is the minimum. Now, here's an important detail. You notice the key word there is relative. That refers to the idea that while 0, 0 is a maximum, it's only a maximum within that range of values, because you can see that over here, eventually the function does go above that point, and it continues all the way up to infinity. So the points 0, 0 or 0, 0 is a relative maximum, which means we just make the font a little bit bigger. The magic word there is relative. The largest point within a given interval. To -4 is a relative minimum, and that's the smallest point within a given interval. And also terminology-wise, a relative minimum or maximum is also known as a local maximum. A relative minimum is also known as a local minimum. Now, sometimes a function does have one point which is greater than every other point within the same function. So if a point is the largest, is a maximum for the entire domain of the function, it is said to be, instead of a relative, a global or absolute maximum. If a point is a minimum for the entire domain of the function, it is said to be, as you can probably guess, a global or absolute minimum. All right. So a point can be a maximum or a minimum, but then we make sure we need to specify whether it's a local or relative or a global or absolute. The function can have many relative minima and maxima, but it can only have one absolute minimum or maximum. So oh, I just realized they want us to specifically mention that this idea of a relative maximum or relative minimum occurs over an open interval. Okay, so let me add that in here. I missed that. A given open interval, here a given open interval. And here they're reminding us about the plurals, that the word relative also means local. It's the same thing. So, oh, here we go. Now you got these three. Now, of course, here we don't know yet how to actually find these extrema. Instead, we're looking at it ourselves and seeing where it appears to reach a minimum or maximum value. So now this one, you can see by the way it looks, you can see that the 0.3 comma 2 is a relative maximum. Over here, there's a relative minimum at the origins. All right, so I guess we can cut it off here. Next time, we'll be diving more deeply into this. We're going to find out exactly how to identify the relative maximum and minimum. And we'll find out that basically what it ultimately boils down to is taking the derivatives of these functions and setting them equal to 0. But we'll get into that next time. So I'll see you then.